In Korea, where I live, math is widely taught to children in cram schools from a young age. The curriculum is mainly focused on shoving equations into your brain and developing muscle memory for test problems. There's nothing wrong with this score-based approach to math, but I think this makes a lot of us miss out on the charm of these topics, especially ones like trigonometry. So in this video, I want to present to you the foundations of trigonometry by demonstrating where the ideas originate from and what we can do with these tools. Specifically, I want to talk about radians and why pi appears everywhere, the special angles and why they're special, the unit circle and how it lets us compute for angles greater than 90 degrees, and how almost all identities can be inspected with the unit circle. Before we delve any further into trigonometry, I want to introduce a key idea into why it is so important. At first, trigonometry seems sudden and unprincipled. After all, how could the ratios of a side of a right-angled triangle be so important to all of math? The key aspect that makes trigonometry important is that it allows a connection between angles and side lengths, which are the two most important unknown variables of modern geometry. If you think about it, these are the only two things we usually care about in finding. By connecting the two variables, we are essentially allowing ourselves to combine these two seemingly unrelated pillars of geometry into one. One of the first things a student will learn in a pre-calculus class is the radian measure of an angle. It's commonly taught as a product of multiplying pi and dividing by 180 to the degree measure. For instance, 60 degrees would be pi over 3, 45 would be pi over 4, 90 would be pi over 2 radians. The radian value is a value that, when multiplied by the radius, produces the arc length of that section of the circle. This would mean a full rotation, or 360 degrees, is equal to 2 pi radians, as the arc length of the entire circle would be the perimeter, which is 2 pi times the radius. Now, most explanations would stop here, but there's a lot more to the story. First, why would we even use radians in the first place? It's because the most important aspect of the radian measure, outside of providing easier computation in circles, is that it is unitless. It's a ratio, meaning the value is always a pure number. Degrees, on the other hand, has a unit because the value is artificial. It's a ratio out of 360, but the value 360 is just chosen because it has a lot of factors. This is why we use radians over degrees in calculus and higher order math. For instance, we can use this really cool process called the Taylor series to convert sine into a polynomial. This yields this crazy looking result, which may seem like pointless complication, but is actually very helpful for analyzing sine. The thing that is in this polynomial, the value of x, can only be in radians, because if we had a value of x in degrees, sine x would also hold a value in degrees, which is absurd. Radian measures are most of the reason why we see pi everywhere. We see pi in these chaotically beautiful equations where they just pop out of seemingly nowhere to complete this perfect expression. Another commonly overlooked topic is how we derive trigonometric values for 30, 45, and 60 degrees. These are commonly known as special angles because of how easily they can be computed with the proper setups. For 30 and 60 degrees, we take a standard equilateral triangle and cut it in half. Using the Pythagorean theorem, we can construct a triangle with 30 and 60 degrees with complete side lengths, which we can use to fill out the table. Now we use the fact that 90 plus 45 plus 45 equals 180. This is important because it lets us construct an isosceles triangle with 45 degrees. Using Pythagorean's theorem, we can find that the hypotenuse has a length of root 2, which allows us to fill up the rest of the table. Just to note, the special angle values will stay the same regardless of the size of the triangle because we're just measuring the ratios. Let me ask you a question. What is the value of sine 120? Well, if we enter this into a calculator, we can see a positive result, and anyone experienced in trigonometry could confidently answer that it's the square root of 3 over 2. But how are we getting this value? I mean, if you think about it, we can't actually construct a right angle triangle for any angle greater than 90. So how can we have a value for sine 120? The answer lies in the unit circle. The unit circle, as the name suggests, is a circle with radius length 1. You can easily show this on the coordinate plane. Now let's take the coordinates of a random point on this circle, let's say xy. Now let's consider the angle of the line that goes to xy from this initial side from 0, 0 to 1, 0. Now because this is a right angled triangle, we know that the value xy is actually equal to cosine theta sine theta. Hence the point xy on the unit circle can be rewritten as cosine theta sine theta, where theta is the terminal angle, or the angle between the line and the original line of 0, 0 to 1, 0. The cool thing is that now we can use this for values like 120 degrees. We can see that in this case, both cosine 120 and sine 120 exist on the actual coordinate plane. Cosine seems to be a value between 0 and negative 1, and sine seems to be a positive value between 0 and 1. Now you might ask if we're even allowed to do this. Can we bend and extend the definitions of math the way we want? The answer is actually yes, absolutely. You can see it done all the time. Just think of negative numbers. How can you actually comprehend values that are less than nothing? Or negative multiplication. How are you going to add something to itself a negative number of times? Pushing the boundaries of math like this actually helps us do more with it. Trigonometric identities. I think identities in trigonometry are equivalent to dates in history for students. They are commonly illustrated as concepts and shortcuts to memorize. And true, many of these are very useful and difficult to get an intuitive understanding of, like the half-angle identities. However, a lot of these are instinctual and simple when you inspect them with the help of an imaginary unit circle. In this chapter, I will prove some of the most fundamental identities of trigonometry with the unit circle and show you how it can be used to analyze most identities in a very efficient and simple manner. The first identity I want to cover is the Pythagorean identity, or how the sum of the square of the sine and cosine values of any angle is always 1. The usual method of proof includes heavy algebra, the important idea being that the Pythagorean theorem can be used to convert the opposite and adjacent sides to the hypotenuse. Now, we can take that same Pythagorean idea to the unit circle to simplify this process a lot more. We already know that we can construct a right angled triangle with side lengths sine and cosine theta for every single theta on the unit circle. Now we just have to apply the Pythagorean theorem to see that the identity holds. We know that all angles have to exist at some point in the circle, so the identity has to hold true for every single angle. The next identity, the tangent identity, is also very simple. It provides a very easy way of relating all the trigonometric functions with each other. We can investigate this in a unit circle. We can see that the tangent value for an angle is y over x, which, as we know, is sine theta over cosine theta. Now, we just covered two important trigonometric identities with the unit circle. However, the unit circle isn't just limited here. It's like the flex tape of trigonometry. It can be applied mostly anywhere. For example, say I encounter the angle sine identities. Well, I can visualize this on a unit circle as an angle going the wrong way, or a reflection across the x-axis. Or the angle plus pi identities. I can visualize these as a line extending in the other direction to the other side of the perimeter. It's a reflection across the origin. My point being, many of these trigonometric identities can be explored smoothly using just the unit circle.